apologize to the class. We hadn't realized it because I really thought that it was a computer problem, but this setup has been problematic all summer, and other people have now complained about having problems with it. So there wasn't anything much that we could do here. We have been working with the CF, that's the computing facility here, who's in charge of all of the AV. And, they're working with their vendors, but I don't think we yet have a final solution here. Okay, that's perfect. Thank you, Ian. Great. So, what I wanted to do was to give you an overview of what we're going to be talking about in this last full lecture. I'd also like to leave time for questions, general questions about astronomy. But today, I'd like to focus on the universe at large. So we're going to start out with a discussion of something called Olber's paradox, which is a funny question: why is the night sky dark? Then we'll talk about universal expansion, as learned through the work of Schleifer, Leavitt, Hubble. And then we'll go over Hubble's law and universal expansion. We'll talk about galaxies and clusters of galaxies. Oh, here, I guess I haven't put on the microphone, so it's on record. I'm sorry. Do we have it here? I guess so. I don't see one. Yeah, I don't see one here.
Yeah, okay, I'll put it here.
Okay. Okay, so let's see how this goes. So as I said, we're focusing on cosmology, the universe at large. So after we talk about some general questions like why is the night sky dark and the discovery of universal expansion, we will then discuss Hubble's law, dark matter, and we'll go to the theoretical description, which really comes from Einstein's equation. We'll talk about black body radiation, which verifies that the universe is expanding. And then we'll talk about the discovery of universal acceleration. Now, today isn't the first time that the universe is accelerating. It also went through a period of very dynamic, high-rate acceleration early on. And we refer to that as cosmic inflation. So we will end on that note, where we're trying to relate quantum mechanics and particle physics to gravity and the early days in the universe. So I'll let you take one more look at this, because we're covering a lot, and I just want to make sure you have a good overview. Okay. And with that, I'm going to do most of today's lecture on the board. So let's bring the screen up. Mute the display. And bring up the lights. So this may seem like a kind of a funny question, right? If somebody asked you this when you were 5 years old or 6 years old, what would you say? Why is the night sky dark? Because there's no sun, yeah. You know, the sun is up. You know, obviously the sun isn't actually, sort of moving around us. We're spinning. And so sometimes we're on the side of the earth that faces the sun, and sometimes we're not. And that seems like a pretty good way of understanding night and day and darkness and why we have a bright sky in the daytime. But is that really adequate? Well, it turns out that by considering this very simple question in the context of the universe as a whole, we can actually learn something interesting. So before we address that question, let me just start out with what people often refer to as cosmological principles. So we'll come over here. Well, the invisible cosmological principles. Here we go. Okay, we've discussed these a little bit earlier in the semester. The basic idea is that we're taking a turn away from old-fashioned ideas that we are special, that the sun is special, the earth is special, we are a special population in terms of the overall scale of the universe. So what the cosmological principles say is that on average, the universe is the same from place to place. It's just like having homogenized milk. I don't know how many of you have ever gotten milk that's unhomogenized, where you have the cream on the top. Is that something people are familiar with? You know, these days you tend to get something that already has been homogenized so that the milk looks pretty much the same from place to place if you see it in a clear container. But in the old days, when people would deliver milk to people's houses, you would find cream on the top. So there was a special place, and if you liked cream, you could get that cream right from the top of the bottle. Not anymore. For the universe, the idea is that we're not in a special place. All places are about the same. Nobody's in a special place. Okay, so, and let me put over here the words on average, because that's important. On average, we have homogeneity. Which is simply that the universe is the same from place to place. Now, this certainly isn't true on small scales, right? Because, for example, there's a difference from being here and being, let's say, at the New England Aquarium. And there's a difference between being there and being at the top of the Empire State Building, right? You can go to many, many different places and know that you are in a place that's different from the place you were before, because on the scale of the Earth here, we don't have homogeneity. We have differences from place to place, oceans, mountains. But in the universe, if you look up in the sky on average, if you imagine traveling many millions of light years from Earth and you were on another planet, you would look around and you would say, you know, this is very similar to where I was before. There are galaxies. Galaxies have globular clusters. There are planets orbiting stars. And if you're an astronomer there, you would discover similar things to what astronomers here discover. Not the same things. There very likely isn't another place that's exactly like Earth that has people exactly like us sitting in a classroom at this time, right? But on the average, very similar. Now, there's another idea, which is isotropy, which tells you that things are the same whatever direction you look in. On average. So the universe is the same from direction to direction. So it's certainly true if we look in some directions, we see things that are different, like maybe we'll see a cluster of galaxies in one direction, and in that direction we might have to look a little bit further to see a cluster. But on average, the density of clusters in one direction is the same as it is in another direction. In particular, in our galaxy, there's a direction we can look at toward the galactic center where it gets very dense with stars. But that's okay because that's local. If you really look farther away, many millions of light years away, hundreds of millions of light years away, and you average out over what you see, you'll see more or less the same thing in all directions. So that's isotropy. And you can show that if you have isotropy in all directions, and that's true at different points in the universe, that forces there to be homogeneity. Now there's one other element to this that people seem to have taken for granted for a long time. And that is, do we live at a special time in the evolution of the universe? So in other words, if we had been born, if the Earth had existed, and we had been born several billion years ago, would things be, on average, in the universe, the same? Well, maybe our own solar system wouldn't be the same. You wouldn't want to be born here 5 billion years ago because I think in that case you're actually coinciding with the formation of the early sun, right? So we wouldn't have this nice planet on which to live. But someplace, probably not too far away from us, or from where the sun was, we could find a place that would be very similar to the place we happen to sit in the universe, at least on large scales. That on average things would look about the same number of clusters, same average number of clusters, etc. And that if we were born 4 billion years from now or 5 billion years from now, the same thing would be true. And you could go further into the future and further into the past. In other words, the universe may look the same, and this is sometimes called the strong cosmological principle. The universe looks the same with regard to time. That is, it looks the same from time to time, on average. Now, do you believe all of these? Does this all seem right to you? These cosmological principles?
The last one, is it saying that the universe looked all different, but its different was the same everywhere?
That's a very good question, because we've been talking about the evolution of the universe, right, in class. So in a sense, we kind of already know that this last one isn't the case.
Okay.
But we're kind of privileged that way because if we go back to what we were talking about last time, the Great Debate, they actually didn't know anything about the history of the universe. Yeah, if you'd like to, you can just take that now. Okay. Later on we can use it for a video, but not until the second part. So they didn't really know that. And in fact, Olber's paradox is a way of perhaps coming to that conclusion. So let me just tell you what Olber's paradox is. And as I said, it seems natural that the night sky would be dark, but I am going to give you an argument now that says that no, the night sky shouldn't be dark. We should be burning up with radiation. We should never have been able to form. Because if these three principles are true, that the universe is homogeneous, isotropic, and the same from time to time, on average, then it would be impossible for creatures like us to be here. So let's imagine that we are here, and let's imagine a sphere all around us, And let's suppose there's a certain density of stars. So rho is the density of stars. And now let's imagine that we take this sphere and we consider a shell of the sphere, a spherical shell, spherical annulus. So imagine this now, all around you is space. Imagine the sphere all around you. And just take a shell that is a certain distance r away from us. And you can ask yourself, how many stars are in the shell? How many stars in the shell? And you can ask yourself, what is the flux that you get from each star? Okay. And since we can do anything we want with this imaginary universe, let's just make it easy for ourselves and make all stars the same. Okay? If you want to make it really complicated, first do what I'm doing and make all stars the same, and then do the same thing with any new kinds of stars you want to introduce. And it'll be the same argument. So we're going to put a star over here, and we're going to say the star has a certain luminosity, and there are stars all throughout this shell, and they all have the same luminosity. So what is the flux that we get from one star? This is by way of review, right? What is the flux from one star? You're going to say it, right?
Luminosity over 4 pi d squared.
Okay, it's the luminosity over 4 pi times the distance squared. What distance am I showing you here?
Sun?
Yeah, well, just this r. I'm just looking for that simple thing, right? You're a distance r away from the sun, and therefore it's L over 4 pi r squared. So you can consider other shells if you want to. Let's do that. In fact, you can imagine many, many shells over here. Just go out and further out and further out, right? What happens to the flux of stars from the outer shell? The outer shells. Is that flux the same as the flux we get at this, from this shell, which has a radius r? No. The bigger r is, the less flux we get. So as we look to the outer shells that have larger values of r, we get less flux. And that makes sense, right? That you get more flux from things near you. We get a lot of flux from the sun. We get much less flux from Alpha Centauri A. Even though it's a star comparable to the sun, it is more than a parsec away, and therefore it's a lot dimmer to us, because r is bigger. Instead of 1 AU, it's a little over a parsec. So it's more than 200,000 times farther away from us. So you get less flux as you go out from each star. But what about the question of the number of stars in the shell? So to get the number of stars in the shell, let me call that n, right? To get n, we need to have the density, and we need to have the volume of the shell. So now we're talking about the volume of a spherical shell. And that volume is equal to 4 pi r squared, where r is the radius of the shell. And the shell has some thickness, which I'll call delta r. So it's 4 pi r squared times delta r. Does that make sense to you, that that's the volume? I'm not going to ask you to repeat this argument, by the way, so don't worry about it. But I'm just trying to make a point, which you'll see in a moment here. Okay, so this is rho times 4 pi r squared delta r. So what happens to the number of stars in a shell as you go further out?
Grows. It grows.
It grows, and it grows like r squared. So what I can do is I can ask myself, what is the flux that you get from the whole shell? Right? That's going to be equal to the number of stars in the shell times the flux that you get from each star in the shell. Right? And that is going to be, oh, I'm sorry, I forgot to put a factor of rho here. The number is rho times the volume, so it's rho times the volume. So what I get over here is rho times 4 pi delta r squared times the flux, which is the luminosity of each individual star, times 4 pi r squared. And a very nice thing happens here. Do you see what's happening? I'm getting a cancellation. What you're finding is that the number, I guess it was the blue that was still working a little bit. You have 4 pi here, 4 pi there, r squared here, r squared there. And the flux doesn't depend on r at all. In fact, the answer is just rho times the luminosity of the star, each star, times delta r. So if you consider 1,000,000 shells, each of them with a thickness delta r, each shell adds that amount of flux. Each one. So now you have 1,000,000 times that flux. But nothing stops you at 1,000,000. The universe doesn't have a limit in size because it has to be the same every place, so there's no boundary, right? So you can go out 1,000,000,000. And then you have 1,000,000,000 times that flux. Or go out 100 billion, and now you have 100 billion times that flux. In other words, the flux from each shell as you go further and further out is the same. So when you add it all up, including shells that are very, very far away, you keep getting more and more flux. In principle, there is an amount of flux that's totally unlimited, and it's coming in toward us, right? Wherever we are, whatever point we put ourselves in the universe, we would have an unlimited amount of flux reaching us. It would be very hot. It would be very filled with energy, right? Creatures like us couldn't exist. But we do exist. Does this depend on whether it's day or night? Does it depend on whether you're facing the sun or not? No. The sun would be giving you just a minute amount of energy compared to, the rest of the universe. So according to this argument, the rest of the universe is giving us so much energy that we shouldn't exist. And because we don't have a lot of time to do this lecture, we won't spend as much time as I would love to having you think about this. But let's spend at least a minute or two. What are the ways around this? What are some of the things that might make this not true? Yes?
Luminosity is equal to 4 pi r squared times the constant times temperature to the fourth. So it still takes into account the distance.
No, that's the radius of the star. In that formula, you're looking at the radius of the star. But that's, so at first you might think of that, right? But that's not the same r. That's not the distance between you and the star. Right. Any other ideas about this? Yes, Rainbow.
If the universe is finite, then even though we don't really know where the boundary is and it's still really, really, really big, we can't make the argument that there would just be billions or trillions or however much luminosity there is.
Right. That's actually a very powerful argument. What if the universe is finite? So you can't keep going out in shells, right? There's no way. But think about it this way. If the universe is finite, unless you're very clever, and I think Einstein was very clever in some ways, you're going to violate homogeneity, right? Because could you imagine sitting on the boundary of the universe? You know, if you keep going out and out and out and out, and suddenly you say, I can't go anymore, this is the boundary, right? There's definitely some kind of violation going on there of homogeneity. So you really have to think very carefully about how the universe could possibly be finite, and yet every place looks more or less the same. It is a violation of homogeneity, and maybe that's the solution, that it's a violation of it. But not only is it a violation of it, it's one that is really difficult to figure out how it would work, right? Yeah. Uh-huh.
Well, our shells are not stable. Like,
Uh-huh.
everything is moving away. So what's in the shell this second is not in the shell the next second.
Okay. What you're getting at is the expansion of the universe. Once you realize that part of this is wrong, and in fact that the universe is changing, there was actually an event, the so-called Big Bang, that happened 13.7 billion years ago, so that the universe was very different then from what it is today, and that the universe is expanding today. There are several subtle elements to this that feed into trying to understand Olbers' paradox, and there's a lot of discussion of this, but ultimately it hinges on this, that these cannot all be true. Astronomers, if the night sky is dark. So this is really pretty amazing, because mostly to derive general results, you need to do experiments, you need to do observations, you need to do calculations. It can be really hard, right, to establish any new research result. And this is a result which is very, very large. Just on the fact that the night sky is not bright, that the night sky is dark, we know that something is wrong with this set of assumptions. We may not know exactly what it is. We can even have discussions about exactly what it is, as people did. This argument is several centuries old. It predates our understanding that the universe is expanding. But something's wrong. And today we know that we can relate the thing that's wrong to the fact that the universe is not really the same from time to time. It was different 4 billion years ago, it was different 10 billion years ago, and it will be different 10 billion years from now. Okay? So, very simple thing. Why is the night sky dark? You can have fun asking your friends this and telling them that actually, from the fact that the night sky is dark, you can learn about the universe at large. So that is Olbers' paradox. And now let's talk about this expansion of the universe. Well, to say that the universe is expanding, first let's see what we mean by that. Okay? What we're talking about is the universe on large scales. So it's not expanding here in this room. If you took the expansion rate and asked yourself, well, how long would it be before my head was twice as big, right? That's not a good question to ask, because your head is not going to get twice as big because of the expansion of the universe. The room is not expanding. The Earth is not expanding. The distance between the Earth and the Moon and the Earth and the Sun, those are not expanding either. Even the distance between Milky Way and Andromeda. These two galaxies are gravitationally bound to each other. They attract each other. And given their present-day trajectories, we're fairly certain that they are at one point going to collide with each other. So they are not moving farther from each other with time. So what we mean, though, is that on large scales, if you look at the velocity of galaxies that are far removed from us at, let's say, tens of megaparsecs, hundreds of megaparsecs, those are moving away from us and away from each other. That in a sense, the entire space that contains all of these galaxies is expanding. So let's talk about how we know that. Because the whole emphasis of this course has been not trying to just memorize facts, but to understand where these ideas and results come from. And this is a pretty huge result, right? That the universe is expanding. And therefore, you are right to expect extraordinarily strong evidence that this is the case. You should not accept this without strong evidence. So let's start with the first bit of evidence, and we happened to mention it last week. If you remember, we were talking about our place in the universe, and we talked about the Milky Way. And in the 1920 debate, the so-called Great Debate, the exact size, structure of the Milky Way was up for grabs. People were trying to understand it. And they were trying to understand nebulae. And they realized that based on the work of an astronomer named Slipher, so Slipher is the first name that comes into this, that many of the nebulae, in fact, apart from Andromeda, virtually all nebulae, were moving away from us. And even that the ones that were farther away were moving faster. So, well, I can't say that actually. Let me not say that because it would not really have been possible to establish this without really knowing the relative distances. So let me say something that is more close to what Slipher actually did. He said that the velocities are such that the nebulae are receding from us. Now, how did he do that? How could he tell that a nebula was moving away? Could you do that? At this point, with what we've learned this semester, suppose somebody had you go out to a telescope, and I'll give you a hint by saying the telescope has a spectrometer. Okay, so you can break up light into its component wavelengths as it comes in to your detector. Would you be able to say whether a nebula is moving toward you or away from you? Yes. You would look for redshifts. That's right. So you would look to see if you had a spectrum. Well, this is a kind of a strange spectrum here, okay? But if you had a spectrum, and let's suppose this line has a wavelength, lambda 0, when you're in the laboratory, what you would do is you would measure the wavelength of that line as it comes to you from a nebula, and you'd subtract that from lambda 0, and divide by lambda 0.
Can you read
Now,
which
if-
one is the observed one?
Well, 0 is the one in the lab. So let's suppose this is a line of neon, and you have a neon tube, a tube with neon gas with you in the laboratory, and you look at you take that light, you pass it through the spectrometer, and you look at where you see the distribution of lines. You say, well, this is a line I see here in the laboratory to have a value lambda 0. Okay, it would be some number of angstroms. But now you're not in the laboratory with the neon tube, you're at the telescope. And the source of this neon line is a nebula. That may be very far from you. It's certainly not in your laboratory, it's not on Earth, it's not even in the solar system. Someplace well beyond it. And you measure, you say, look at that spectrum, that is reminiscent of neon. But when I look at the lines, and let me focus on this particular line that has a wavelength lambda 0, there's something a little wrong. The wavelength I measure is a little off. It's off by an amount, lambda minus lambda 0, or delta lambda over lambda 0. And if lambda is greater than lambda 0, we call that a redshift, because you're shifting toward longer wavelengths, and on the visible spectrum, red are the longer wavelengths. So you say you have a redshift, delta lambda over lambda 0, and if the galaxy is not moving too fast compared to the speed of light, this is proportional to V over C. So you measure this, and that tells you the velocity. You measure that and you learn the value of the speed away from you. Now, police officers do this, right? Because what are they doing with these radar guns? They're measuring a Doppler shift. Meteorologists do this when they're looking at the motion of air masses. They're looking at their Doppler radar. And astronomers do this all the time. We do it to measure how fast a star may be moving when it wobbles because there's a planet around it, right? That's using the redshift. And we do it when we're looking at a distant nebula to find out what its speed is relative to us. If the wavelength is shorter than the wavelength would be in the lab, then that's a blue shift. The object is moving toward us. And if it's redder, it's a red shift. It's moving away from us when the wavelength is longer. And if you're watching an orbit, you're going to see a blue shift, and then you'll see a red shift, and then you'll see a blue shift, and then a red shift. So you'll see this periodic phenomenon going back and forth. But with these distant nebulae, we don't see that. We see, except for Andromeda, a red shift. So what Slipher established is that these nebulae are primarily moving away from us. And that's something that's well established. At this time, not only has Slipher done that, but probably thousands of other astronomers have made the same measurements and have validated them and have also checked that this works at bigger distances, now that we know how to measure distance. And the way we learned how to measure distance was from Henrietta Leavitt, because of what we discussed last time, the period luminosity relationship. So this is for Cepheid variables. So if you measure the period of a Cepheid, because there's a relationship between the luminosity and the period, we can figure out how luminous it really is. Its intrinsic luminosity And then by comparing that luminosity with the flux we actually get from the star, we can compute the distance. So for Cepheid variables, we can compute their distance just from measuring their period. And fortunately for us, Cepheids are bright stars, so we can see them even in other galaxies. So this was a tool that told us how we could figure out how far away Cepheids are. And if a Cepheid happens to be associated with a nebula, that tells us how far away the nebula is. So now we come to Hubble. And this is the person Hubble, Edwin Hubble, who found Cepheid variables associated with the nebulae and was able to measure the distances. So he used the Leavitt law for Cepheids to measure the distances to the nebulae. So there was another piece of work in between, right? The redshift was part of it. Looking at the period luminosity relationship was another important part of it. And that itself took a lot of work to discover, right? This was work that, as we discussed last time, was done here in the Harvard plate stacks, but it has been done now many, many times over in different ways. In fact, the Hubble Space Telescope, named after Edwin Hubble, had conducted or has conducted a so-called KEY project, very important project, to study Cepheids in many different galaxies. And Hubble brings unique, the Hubble telescope brings unique capabilities to this because you have great angular resolution and very good photometry, and you can measure the period very, very well, and you can measure the flux very, very well. And so you can really use, both calibrate and use the Leavitt relationship. So this is a pretty remarkable story. And, you know, I hope one of the messages you take away from this is that we can do remarkable things with very simple tools, right? I mean, can you imagine just establishing that these nebulae are actually very far from us? You know, millions of years, many millions of years away from us. And that they are systems as big as the Milky Way, some of them bigger. And that they are moving away from us. That this really, remarkable as it seems, that creatures like us could figure that out, we're doing it with very, very simple principles. Very, very direct, and in a sense, easy to understand science.
Why does a longer period increase the luminosity?
Okay, I wouldn't say that a longer period increases the luminosity. What I would say is that the systems that are giving you this oscillation are stars, and they're very evolved stars. So as it turns out, before people understood what made them luminous at all and what stage in their evolution they were at, none of this was understood at the time Henrietta Leavitt was doing her work. It was simply an observation that when you had a bunch of them all in one place, like in the Large Magellanic Cloud, the ones that were brighter are the ones that had longer periods. So to begin with, it was simply an observation, and that observation was what led to the graph that we talked about last time. Now, why that should be the case, that comes down to understanding more about stars and how they act. Well, it's not so much, that's a good question. Of course, most stellar properties are related to mass, right, as we've discussed. But these Cepheids are at a very special point in their evolution where as they evolve, they're also getting brighter. And so it simply has to do, the period is a pulsation period. So these stars are expanding and contracting, expanding and contracting. And the thing that is happening here is that you have a longer time to expand and contract, a longer period for the brighter stars among Cepheids. And there are similar relationships for variables that are similar to, but not exactly the same as Cepheids. But that's really a crucial question, and that's the question that a scientist asks, right? You have this relationship which we can use, and people have used it to establish these distances. But if you really want to understand what's going on, why that relationship works, you want to get down to the underlying science of it, the underlying physics. Remember last time we were also talking about it with supernovae, that we can use supernovae as great distance indicators. And yet we don't really know what kinds of systems they explode in, right? But just because of that, we're working very hard to figure it out. Okay, any other questions about this? Okay, so what I'd like to talk about now is putting this and Slipher together, because Slipher established the velocities of these nebulae, and then Hubble established the distances. So he was able to do a very simple thing. He could say, okay, I now have the distance and the velocity. Let me make a table. Right? You probably have to do this in almost every lab course that you take, right? You measure one variable, and you measure another variable for the same object, and you look to see if they're related. So you can make a table of velocity versus distance, and you have some V1, D1, V2, D2. So Slipher, Hubble. And of course, Hubble's a very smart guy. He's not going to just rely on somebody else's measurement of the speed, right? You know, you really want to put this all together. And so you keep doing this for many different nebulae. And what you find out is what I started to give away before, which is that the more distant they are, the faster they're moving away from us. So if this is the distance measured in megaparsecs, and if this is the velocity measured in kilometers per second, there is a relationship. You put the V for one of them together with the D for the same one, and you keep doing that for each one. And what you find is that this appears to be a straight line. For Hubble, that's what it appeared to be, a straight line. So in a sense, that's kind of remarkable. Slipher first said they're moving away, and now Hubble said, yeah, they are moving away. And the ones that are moving fastest are the ones that are furthest away from us. Now, does that seem strange that the ones that are moving fastest are furthest? Why would that be?
Gravitational forces.
Well, that's an interesting question. Gravitational forces must be involved in this whole process because all these galaxies and clusters of galaxies clearly are experiencing gravitational interactions. But that's not directly related to why they're moving faster when they're farther away. In some sense, we can relate this to Einstein's theory, so you're actually on the right track here. But the reason they're moving faster as they're farther away is a little bit different. In fact, it's something that gives us a way of describing the expansion, right? Some of you were with me when we had a session together, and maybe once here in the class as well, where we talked about this. And the example that I kind of like for this is a sort of a jungle gym. Imagine this is three-dimensional here, okay? I'm not very good at drawing the three-dimensional, not very good at all at drawing the three-dimensional elements of it. But you can imagine a three-dimensional jungle gym. How many of you have been on a jungle gym when you were younger? How many of you have been on a jungle gym recently? I don't know if they make them big enough for us. But anyway, you're on a jungle gym, and imagine you're in a really crowded playground. So there's somebody at every vertex of this jungle gym. Okay? And I'm not even going to try to make them look like people. Okay? Just imagine at every vertex there's a person. And now, let's consider a situation where this jungle gym starts expanding. Let's suppose it doubles in size in 1 minute. Now, this would involve some pretty fancy stuff because each of these bars would have to double in size, right? But, maybe they're constructed in such a way that, you've seen these tubes where you can extend them, right? So imagine you can extend this, and it's going to double in size in 1 minute. So now you have somebody over here, and let's suppose this starts out to be just 1 meter in length between these two. At the end of a minute, they're going to be farther away from each other. How far will they be? If it doubles in size every minute, you're 1 meter away to start out with. How far away will you be after a minute? 2 meters. Yeah, it's not a trick question. It does seem kind of weird that the whole, velocity is different at different distances, but it's not a trick question. So for these people, if you start out at 1 meter, you go to 2 meters apart in 1 minute. But what about if you started here, same place, but now you're looking at your friend who's over there, and the initial distance between you and that friend was 2 meters. After a minute, how far is that friend going to be? 4, right. So if you start at 2 meters, you go to 4 meters. And similarly, what if you start at 3 meters? What happens after a minute? Gone to 6 meters. Right? Now all that's happened is that every tube has doubled in size. But the relative distance between you and the next person has only increased by 1 meter. So your speed is 1 meter of increase per second. But the one here, the next one away, has increased by 2 meters. I guess I said a minute. 1 meter a minute, let's say. To increase by 1 meter a second, if you're on a jungle gym, would be pretty scary. So let's do it in minutes. So for your friend who is 2 meters away to begin with, now they're 4 meters away. So you've moved from them 2 meters in a minute. And from the one that was 3 meters away, you're now 6 meters, right? So now you've moved 3 meters apart in that minute. So you see, the speed that you measure for your friend, suppose you had a Doppler radar right? And you're pointing them at your friends who are moving away from you on this jungle gym, the ones who are farther away from you are going to be moving faster with respect to you, and you're moving faster with respect to them. And it's all because this jungle gym doesn't crumple up and it doesn't break apart. If the jungle gym is going to expand at a uniform rate every place, so that distances double every minute, distances between the nearest points double in every minute, then the people on further parts of the jungle gym will be moving away from you at a faster rate. So this is a feature of uniform expansion. So what we see here in the Hubble law is a feature of uniform expansion. That's all it is. So it may seem to you, if you're on the jungle gym, now make this jungle gym really big, okay? Make it, extend across the whole playground. Make it extend across the whole neighborhood, right? It's a huge jungle gym. The kids are on this, and each one looks around and says, everybody who's farther away from me is moving faster. It looks almost like you're in a special place, right? But every single child measures the same thing, only because the jungle gym is uniformly expanding. If the jungle gym would crumple up at some places, suppose it would get warped and, look, instead of like this nice uniform shape, suppose it started to look more like this, these different bars were warping and maybe even doing something kind of crazy like this, then you wouldn't have this uniform expansion, and you wouldn't have the speed being proportional to the distance away. It's because it's a uniform expansion. So it's tempting to think, hey, we're in a special place here, but actually we're not. Everybody in the universe would measure this same law. If they get to a point in their technological and scientific evolution where they're looking at distant galaxies and they become able to measure the distances to those galaxies and the velocities of those galaxies, as we have, they will find the same law. So this is the Hubble law.
Does the math hold up? Like, does it follow the laws of math?
Yeah.
Like, if you take the derivative of that, does the rate? What I can't wrap my brain around is that the rate is the same, but the velocity is exponential.
Well, I don't know if you say that it's exponential. Let me write it out for you as a law, because you may be getting at something else, which is that it could be that you have an expansion, right? An acceleration. This is an expansion. And if you're measuring this distance in megaparsecs and v in kilometers per second, what we can say is that the velocity is proportional to the distance. Maybe I should write that up here a little bit higher for you. The velocity is proportional to the distance. And that means simply that you can write the velocity as a constant times the distance. And this constant is referred to by us, not originally by Hubble, as the Hubble constant. Whoops. And it took decades to measure the value of the Hubble constant. In fact, Hubble got it wrong. Hubble could see that there was a linear relationship, although if you look at his graph, he didn't have that many points. You might even criticize it if somebody came up to you. Suppose you are in graduate school and you're the TA, the teaching assistant who's running a laboratory, and a student comes up to you and says, here, look, I had these few points and they fit a straight line, you might say, I think you better do a few more measurements before you say that. But Hubble was looking at the whole universe, and he could measure what he could measure, and he did the best job he could. He didn't understand everything about Cepheids, so the relationship that he used wasn't exactly the one we would use today. But the basic principle has really stood up with time, that this is an approximately linear relationship, and that V is equal to D times a constant. And after decades of arguments back and forth and many measurements, we finally come to the conclusion that H naught is approximately 72 kilometers per second per megaparsec. So what this means is the following. Let's do an example. Suppose that you're looking at a cluster of galaxies that's 20 megaparsecs away. That actually is the case for the nearest cluster, the Virgo cluster, about 16 to 20 megaparsecs away. Of course, it's a big cluster, so some galaxies in the cluster are nearer to us and some are farther. But let's take a distance of 20 megaparsecs. And then what is the speed that that galaxy, or that the cluster as a whole, let's say, has with respect to us? So you can figure it out, and then we'll talk about it.
I'm worried. Okay. Okay, so that's okay.
Yeah, right, okay. Okay, so what is the answer?
40 kilometers per second.
How much?
1,440.
Okay, let's check it out. Okay, let's just plug in. Okay, well, what are some of the answers people have gotten here? Okay? Okay, say it out for me again.
1,440 kilometers per second.
Okay. Now that's getting up there, right? That's a pretty significant speed. Okay, so it's going to be 72 kilometers per second per megaparsec. I can write the megaparsec just in the denominator here. It's the same thing. Times 20 megaparsecs. So indeed, it's 720 times 2, or exactly this, 1440 kilometers per second. And now think about it. Suppose instead of being 20 megaparsecs away, it was actually 200 megaparsecs away. Then the speed would be 10 times higher. It would be 14,400 kilometers per second. So these recessional speeds can be very high. And the shifts in the lines can be very high. So that a galaxy that's sending us a lot of, let's say, ultraviolet radiation, if it's far enough away, that ultraviolet radiation may appear in the red part of the optical spectrum. Of course, that would correspond to a very large redshift. So larger velocities, larger distances, larger velocities, larger redshifts. Okay, have any questions about this? Yes.
Regarding all expansion theories, where does the matter come from?
Oh, wait, say that again? I'm sorry, I didn't hear you.
For all expansion theories, where does the matter come from?
Well, that's that's a very good question. The The way we understand the expansion of the universe, and this is supported by our discovery of black-body radiation, is that the universe was actually very hot and very dense in its earliest stages. And so the matter was there already. And it came from a past where it was hotter and denser and in different forms. And through the history of the universe, it evolved to eventually form nuclei and atoms and stars and galaxies. So the matter is there. There actually was a very serious proposal in the years after the discovery of the expansion that simply could not accept that things could have been that much different in the past. A sort of a holding on to the perfect cosmological principle. And so there were a group of scientists who continued to argue this until very recently. In fact, some may still argue it, that actually, rather than have the universe change from time to time, maybe it looks the same at all times, and in order to explain that, if galaxies are moving farther away from each other, they said in the middle of galaxies, in between, in the space between, matter must be created. And that this matter would eventually also form galaxies, and so over time, the density of galaxies would stay the same. So they, in order to avoid believing in the genuine expansion of the universe, they developed a theory that involved the creation of matter, which violates a fundamental rule of physics as we understand it today. And so that theory has been discounted, and I'll tell you in a little while how it was discounted. But in fact, one of the main proponents of that was someone called Fred Hoyle, who was a British scientist and a writer. And Fred Hoyle was a very, he explained astronomy very well to a popular audience. And he was on a radio show. I don't know if we can get a clip of that. Maybe during the break we'll see. I don't even know if a clip of that exists, because I don't know if these things were recorded back then. It's the first time I'm thinking of actually what it must have sounded like. But apparently he was asked about this, and of course he propounded his own steady state theory, but to make the other way that the universe had some kind of a beginning, to make that sound ridiculous, he said, they would have us believe that there was a big bang. And that's what started the universe as we know it. Now today we actually refer to that thing as the Big Bang. And everybody does it, so he made up this phrase to sound ridiculous, and that phrase was adopted by all of his rivals. So we do call it the Big Bang. It would really be kind of fun if we could find a quote of that.
So if we see a light, I don't know, 1 million light years away, and we know it's moving whatever value fast away from us, then we can define the edge of the universe for us.
Well, there's a kind of a horizon for us.
Right,
yes, that is a horizon beyond which we cannot see.
Right.
And that horizon actually changes with time. So it's a very interesting thing. Yes. Now, I want to make one other point here before we stop for a break. But let me just make sure that there are no questions. This is actually fairly straightforward, right? These arguments are very straightforward, but we're dealing with something that is in fact very deep, right? We're talking about the expansion of the universe and what the universe looks like from place to place and the history of the universe. So I'd like to actually bring this back now a little bit more to the history of the universe. Let's actually keep this here. And let's think about looking at galaxies that were once very close together, and they're now separated by a distance d. Okay? And we now know that this would be equal to their, well, let me relate it to Hubble law. V is equal to d times h naught. Therefore, we can say that d is equal to v divided by h naught. Right? Let me write this. I've written it along a diagonal here. Let me write it out straight for you. It's a little bit easier to see. Now I can say something else about the velocity. They have covered, if this is a constant velocity, they have covered this velocity in the time that the universe has been expanding. So v is equal to d over the lifetime of the universe. So let me put these two equations together. If I do that, what I find out is that h naught is equal to 1 over the lifetime of the universe. Many times people will just write that as 1 over t. Now, there were assumptions that went into this. I would not use this as my absolute best answer to the age of the universe because I'm talking about constant expansion. It may not be a constant expansion. There could be acceleration involved here, right, as one example. But this is an estimate. So if I want to know what is the age of the universe, I'll say it is 1 over h naught, and I will say that this is an estimate. It's a pretty good estimate. So now we can figure out what that is, because we know what h naught is. So we can plug that in. Tau of the universe is equal to 1 over 75 kilometers per second per megaparsecs. Okay. And let me just write the units a little differently. I'll put the seconds and the megaparsecs in the numerator and the kilometers in the denominator, and then I have 1 over 75. And you see a nice thing happens over there with the units. Kilometers are a unit of distance, right? 10 to the 5 centimeters. And megaparsecs are also a unit of distance. A parsec is 3.08 times 10 to the 18 centimeters. Megaparsec is 1,000,000 times bigger. So we can actually plug those things in, but the key thing is that it's a distance over a distance, and once we plug in the numbers for what these distances are, we'll have centimeters in the numerator and centimeters in the denominator, and they'll cancel. And so you're left with just a time expressed in seconds. So we're going to derive the lifetime of the universe up until now in seconds. And this is just a little bit of arithmetic, a little bit of powers of 10. So this is equal to seconds times megaparsecs is 10 to the 6 times 3.08 times 10 to the 18 centimeters. Okay? And a kilometer is 10 to the 5 centimeters. And I'll put my factor of 75 down here. Centimeters cancel centimeters. And now you just have to do a little bit of arithmetic here. 6 minus 5 is 1. 1 plus 18 is 19. So you have 3.08 over 75 times 10 to the 19 seconds. And now you want to figure out what that is. So this takes just a little bit of arithmetic, and that's 3/4 times 100. And what you get when you do that is roughly 4 times 10 to the 17 seconds. And remember that 1 year, I'll write it down here, 1 year is 3.15 times 10 to the 7 seconds. So when you figure out what this is, it comes out to be a little over 13 billion years. Anybody do the arithmetic? What does it come out to be?
1.3 times 10 to the 25th.
1.3 times 10 to the what?
25th.
I think maybe you have the 7 going the wrong way. Because it's going to be, you want to subtract 7 from that. So it's 10 to the 10 years. Or you would say about 13 billion years. Okay, is that everybody in agreement on that? So isn't this amazing? We started out the lecture saying, well, look, there's this perfect cosmological principle that says the universe is the same from place to place, from direction to direction, from time to time. And we still think all of our measurements support that it is the same from place to place and from direction to direction, but it is not the same from time to time. That in fact, there was an event, which we often refer to as the Big Bang, that happened a little over 13 billion years ago, about 13.7 billion years ago. And that the universe then was very different from the universe today. I think this is a good time to take a short break, and we'll come back and we'll talk more about the fact that we really do know that this is very likely the correct view of the past of the universe. So what I suggest now is that you get back together in your groups for the project, and maybe Ian and I can come around quickly and just check in and make sure that you're making good progress. See if you have any questions.
I see what it is.
I got
那你下线，而且既然下校这么的话，说明学校你要去这样的话，我真的觉得这特我现在给我老公发这个表情。 老师回了我的表情。我不能跟老师说这个，老师这样打我。不能。老师回我你也是。不能。这真的是要生气。那你不管是你妈妈，那我觉得比我妈妈比你老师还可怕。因为我妈说我不能跟我妈。跟老妈说你好骚。哎，我真的。瑟瑟发抖。挺好看的，这个看我能不能买。然后我就想说，现在一般都是我买衣服，我妈我能不能买？我妈不问我。我妈更喜欢。哎，为什么？
Yeah. But I haven't gotten to that yet. You're good.
Because you're doing the heavy
If I cannot get online, then
Oh, this is the name.
No, I was just curious when I started to read. I was reading about black holes. It made me think of some of your work. It's super cool. Cool. I was reading about how they found black
Thursday, not this one is tested. Yeah, about what? I don't know what the test is. I assume they'll send out something so. Yeah. Do you know what you're going to look at? Huh? Do you know what your guys will do? Yeah, I'm working on how it works. Like how it works and what it's made of. What is it? That's nice. Is that okay? Yeah.
他连计划书1次作业2次，再加上最后发现。 It's on like how stars die too much. I have these thoughts on there, but I don't know if they're very because I'd rather worry about things that
How old were you?
I'll get back like the Academy has something called.
Yeah, that's what.
Let's see how many. 27. So maybe I'll talk for 5 minutes.
Like a semester.
So do you still look good for observing? And are you looking at the or are you allowing anybody to go up there? What's your goal? Yeah, I know.
What did you do?
Everything will be ready.
What do you do bus? Like the class is super chill, but then the test.
I know, I was out then. It was, yeah. Okay, let's get started again. Okay, guys. Okay, let's get started again. About 5 minutes of first lesson. I guess we should bring this in, shouldn't we? Here we go. There we go. About 5 minutes of first lesson. I'll actually answer some of these questions right now. I think
We're 7 people, so it's going to be 35 minutes.
that's right. Okay, let's get started. I had a couple of questions during the break, which I'd like to answer. One of them was to talk about the exam. So let me do that. And then we'll show something else in a few minutes. So in terms of the exam, it will basically be on the assignment that you've had since the previous quiz, right? So it's new material. There will be an overlap in terms of flux. So make sure that you really feel familiar with flux. And for the rest of it, it will be new material. For example, the Hubble law will be on the new quiz. So if you go back to the things we've studied since the last quiz, and the assignments that you've had since then, it's basically that will be on the quiz on Thursday. And what we'll do is we'll start with the roughly half-hour lecture, and then we'll move on to the quiz, and then you can work with your groups. We'll have to figure out how to do that in a way that doesn't disturb people who are still taking the exam. So I'll see if we can line up some spaces for you to work if you are indeed working together on the project. And let me just check in with you. In terms of your groups, do you feel like you're doing well with the project? Okay, I won't ask you for anything before the quiz because I know you want to concentrate on that over the next couple of days, but I will ask that on Friday people send me a little bit of an updated summary of what's going on with their projects. But I don't want to burden you with that until after you've had the quiz. And then next Tuesday will be the presentations. Now, my one concern about the presentations is timing. Somebody asked me about the time. For each member in the group, you get 5 minutes. So a 6-person group gets half an hour. That doesn't mean that you should go, each person 5 minutes necessarily. For example, if you've prepared a video and 4 of you have worked on that video could take 20 minutes, right? And that would be fine, as long as it's clear when you're talking to me and talking to Ian that there was work done by all of the people involved in creating that. Now my concern is timing, because it's going to be very difficult. We have a 3-hour lecture, right? So in 3 hours, I don't think we're actually going to be able to accommodate everyone. And our choice is either to start early, to go late, or to continue on Thursday. And I may send you a Google poll about that. So after Friday, we will send out an email that gives you a chance to sign up for whatever time you would like. And of course, there'll be some moving around, because if everybody wants the same time, we'll have to have some way of making a decision about who gets what time. But also, we'll have to figure out how are we going to manage with the time that we have. And I'll ask you your preferences on that as well. If we vote for Thursday, though, then you would have to be here Thursday. How many of you will still be in town on Thursday? Okay, this is pretty good. So only a few people are leaving. Anybody who's actually leaving sometime between Tuesday and Thursday? Oh, well, that gives us freedom. How many of you would like to actually have presentations extend over both nights? Okay, if you would like that, we can do that. That would actually be a little bit, I think it would make us enjoy the presentations more, because we wouldn't have to make so many jumps in the middle of one night. So that may solve our problem, because that gives us 6 hours for presentations, which is more than we need. And that's great. We can take our time and we can enjoy them a little bit more then. So then the question comes, who is brave and does it on Tuesday, and who does it on Thursday? So I'm hoping that there's not, that there's not just one preference that everybody wants, but that actually you prefer. Some people prefer to go Tuesday and some people prefer to go Thursday. Right now, let me just see, anybody prefer Tuesday? Okay, so we definitely have some groups that'll be ready to go then. Okay, excellent. So let me continue a little bit. Yes, was that a question?
Yeah. So if a student is showing a simulation of, let's say, supernova, does it count into his 5 minutes if he's giving an oral speech?
Yes, it does, because basically, we have about that much time per person. So you should get together with the group. If you have 5 members in the group, then you all have to decide together how to spend your 25 minutes. Okay, so, and actually it's a good idea, I should mention this now, it's a good idea for each group to have a timer. Somebody who's in charge of keeping you on track for being on time. Because as you might imagine, it's kind of hard sometimes to keep yourself within that 5 minutes, and mostly people tend to go over. That's the general trend. And what happens is often the first person goes over, and if we really do have any kind of time pressure, we may have less this time, but if we have time pressure, it's really hard then for the rest of the group. So there should be someone in each group who's the designated timekeeper. You should practice, do it for yourselves, get together and do a practice run. Sometimes you may need to do more than one practice run. And make sure you can stay in your time limit. Okay? And if you have trouble with it, let me know ahead of time. If there's something that's taking a little bit longer, let me know, and we'll see if we can work it in. But what you don't want to have happen is that somebody who hasn't practiced ends up going on, and after 5 minutes, and the rest of the presentation is, pretty well planned out, they're still talking, and after 7 minutes or 8 minutes or 10 minutes, they're still talking. You need somebody to be the timekeeper or the director and say, before you get here, you've worked out all of those glitches. Any questions about any element of the course, what's expected of you? So we're coming down to the end now. I want to make sure everybody is clear on what they need to do. If you do have questions, you can also just send a quick email. Okay, so let's continue then. We are going to be looking at the Nobel Prize lecture of Adam Riess. And actually, Hannah, where are you, Hannah?
Here.
Huh? Oh, there you are. Okay. She actually has a radio interview with Adam that we weren't able to play. But if we can get it playing, maybe for one of the, we'll have a little bit of extra time on the presentation nights. Maybe we can do that. It was pretty exciting, actually, because on the first day of class, Hannah just happened to interview Adam Riess for a radio interview. So it would be great to hear one of our class members do an interview with Adam, who, by the way, was a student here. He was a student of Bob Kirshner, whose book you're reading. But I want to come back to what we were talking about on the cosmic expansion. A couple of points. Let me just make sure this is recording. Yeah. A couple of points. One is that the way to view the redshift when we talk about cosmic expansion is through the expansion of the universe itself. So if light is emitted from one place in the universe, let's say from one galaxy, and it travels to another, the space between these galaxies is increasing, and the wavelength of the light is also increasing. So when we talk about cosmological redshift, we can do calculations like the ones we did here, and that's fine for the small distances. But the thing to think about is that we are looking at an expansion that affects the wavelength of the light itself. Just think about everything as stretching out. Another very important point is that the expansion, the Big Bang, was not something that happened at one point. There is a question that is often asked on exams where people have been studying cosmology. The Big Bang, where was the center of it? Was it someplace in Topeka, Kansas? Was it someplace in the middle of the Andromeda Galaxy? Where was it? Well, it wasn't in any of those places, yet it was everywhere. So in some sense, yes, it was in those places, but it wasn't in one of them. It was everywhere. That space-time itself expanded and continues to expand until today. So it's a little bit hard to conceptualize. These are very deep things, and in some sense, we learn to say the right things about them. But it's very interesting to spend some time really meditating on them and trying to understand what the expansion of the universe really means. Now, for a long time, there wasn't a good argument to say that it was the Big Bang instead of the steady state. But in 1963, that changed with the discovery of the cosmic microwave background. Now, I've told you a little bit about this story. I don't know if you remember. Do you remember Arno and Penzias at Bell Labs in New Jersey with this radio antenna that they were trying to modify to make it work well for radio astronomy, and they couldn't get rid of the signal. There was this little buzz of noise that they couldn't get rid of in their antenna. And they worked very hard. They spent a great deal of time and effort trying to eliminate it, and they couldn't. And because they kept working on it, and because they wouldn't give up until they understood it, it turned out that they eventually published it, and by that time it was known by others that this was actually radiation that came from very early in the universe, the first time in the universe when atoms could form. So do you remember this story? I think this is a really interesting one because it shows what goes into good science, the fact that there's something you don't understand, and sometimes you're not sure if it's trivial or not. I think there must be some simple explanation for it, but if you don't really know what the explanation is and you can't figure it out, you can't just proceed as if it's not a problem. You have to understand what's going on. And they did that, and because of that, they made a major discovery that they weren't even looking to make. There were other people who were interested in trying to understand the radiation that came from the time when atoms could first form and light could first travel freely through the universe. And it just so happened that the discovery was made because of the perseverance of this one group. So there were two papers, one on the discovery, one on the cosmological implications, and the discovery won the Nobel Prize. So that was Penzias and Wilson. Once we knew that there was a cosmic microwave background, this told us much more about the history of the universe. It told us that the universe didn't always look the same, and that therefore the steady state theory was just a theory, but it was an incorrect theory, and that that's not the way the universe is evolving, by creating matter in between the places where there are galaxies. So this was very important. Now I'd like to move topics a little bit to come back to something we considered in one of our first lectures, which is the acceleration of the universe. Now you saw the film Runaway Universe, and you can find it again online. If you want to re-watch that, you're very welcome to do that. And that is an amazing film because it happened to be taken at the time when this discovery was being made. So now I'd like us to hear about the discovery as it was told by Adam Rees years after the discovery was made. Not in the 1990s, but in 2011 when he and Brian Schmidt and Saul Perlmutter, all of whom you met in the film, won the Nobel Prize. So Ian has been kind enough to get this set up for us. Let's see if it will run. There we go. Okay. So let's see. Don't hear the sound. Ian, would you mind coming up and taking a look at this? It looks like you have the sound connected. Let's see. I'm going to bring up the lights again. Okay. Maybe not.
Observations of exploding stars reveal that we live in this very strange universe, not only
Is it loud enough? Let's make sure.
but accelerating. I'll answer Brian what we did wrong.
Okay, shall we start this one again?
I got interested in this subject.
Wow. Okay.
Well, thank you very much. I want to thank the Royal Swedish Academy of Sciences the Nobel Foundation for recognizing our work. I want to particularly thank my colleagues and teammates on the High-Z team, the Higher-Z team, for sharing this science adventure. Brian called it a science fairy tale. I see it as an adventure story. We'll see what you think at the end. I'm going to continue telling the story of how observations of exploding stars reveal that we live in this very strange universe, not only expanding, but accelerating. And now I'll answer Brian what we did wrong. I got interested in this subject of measuring the universe when I came to understand that one could answer really big questions. How old is the universe? How big is the universe? What is the ultimate fate of the universe? By measuring the rate at which the universe expands, and if you measured that very precisely, and also measured it, as Brian described, back into the past to see how the expansion rate changes with time, you actually could answer these questions that seem just like philosophers' questions, were actually something that you can answer with careful measurements of redshifts and distances, as Brian described. So when I started graduate school in the early 1990s, the expectation was that we lived in a universe that resembled either the one on the left or the one on the right. Either we lived in a very heavyweight universe, a very massive, dense universe, whose mutual gravity, the attraction of all the material in the universe, would rapidly slow down this expansion that came after the Big Bang, so that eventually the expansion would stop, the universe would start to collapse, and we would have the opposite of the Big Bang. Brian called it a funny name, but I'll call it the Big Crunch. Or we lived in a very lightweight universe that had such little material in it that it was only modestly decelerating, in which case we would say the universe had escape velocity from itself. Like if you launched a rocket with enough speed, it would get away. And so we could have lived in either of these, or we could have lived in the knife edge case, exactly the right mass that the universe would stop expanding, but only when it reached infinite size. And by the early 1990s, it became clear that our best method for determining which universe we lived in would be to find these exploding stars, especially the ones in the past, that could give us the history of the expansion rate of the universe throughout time. And by measuring the deceleration, by seeing if it was very large or very small, we would in essence weigh the universe to determine its ultimate fate. By the early 1990s, by the time I started graduate school, it was thought that these type 1a supernovae, these stars which had attained the Chandrasekhar limit and exploded, would make great standard candles, although as Brian described, it also became clear that perhaps they were not going to be perfect. The idea behind a standard candle is just a simple rule. If it's bright, it's nearby. If it's faint, it's far. That works very well if they really are all the same. But 1991 really was a watershed year for understanding type 1a supernovae. Nature gave us the bookends of the class. The most luminous one we had ever seen and the least luminous one we had ever seen. And it was kind of hard to ignore that they were not really all the same, that we would have to come up with a way to account for these differences, much in the way that Mark Phillips described in his seminal 1993 paper, that the ones that are intrinsically dimmer will fall faster after they reach their peak. I became interested in another problem that was related to this when I started graduate school, and that is another reason that a supernova could appear faint, not just that it was far away, not just that it was intrinsically dim, but sometimes in galaxies there is dust, and the dust will screen or scatter the light of the supernova, making it look faint and fooling you into thinking it's further away. Now, the kind of dust we're familiar with is more efficient at scattering blue light than red light, which means more red light comes through, and so it also not just dims, but reddens the light. And so there was a hope that you could use this telltale reddening to tell that when a supernova looked faint and red, then it really was not so far away. And so a lot of the foundations of this work was laid by the Kolontololo survey in the early 90s, which collected some of the early foundational data on supernovae to help us begin to think about these concepts. Now, when I started in graduate school, these are my academic parents. We were a very progressive family. Massachusetts was a very liberal state. And so I worked with Bill Press and Bob Kirshner, and we developed a different formalism, a different way of measuring the supernova light curves called the multicolor light curve shape method. The idea was to combine both of these effects. The fact that the supernovae were not all the same intrinsic brightness and that sometimes they had dust in front of them. So that is, we wanted to distinguish when faint meant far away, when faint meant intrinsically dim, so not so far away, or when faint meant dusty, and again, not so far away. And we developed a fairly strong statistical machinery to make these simultaneous corrections, to use measurements of the supernova throughout its whole history, to deal with the relation between different kinds of errors in the data, and to make use of simulations from galaxies to give us extra information about how much of this dust was in the galaxies we were looking at. By 1998, we had added an extra feature, even to be able to make use of missing epochs of data, all in the interest of trying to improve our ability to measure the expansion rate of the universe. And this was a key figure from my thesis. This is one of these diagrams intending to measure the rate at which the universe expands from determining where the line is that goes through the data, but you can see a number of objects which have scattered very far away, in particular in the direction where it looks like the supernovae are faint, and so you think they're far away, but they're really faint for different reasons that don't have much to do with distance. In some cases dusty, in some cases intrinsically dim. And so when we applied this machinery, we found that with many less supernovae, we would be able to make a very powerful measure of the expansion of the universe. The other part of my thesis at Harvard with Bob Kirshner was to collect the first large sample of supernova light curves in the north. The Kolontololo survey was in the south. And by the end of 3 or 4 years of hard work with a 1.2 meter on Mount Hopkins with the CFA crew, we've collected 1,200 observations of 22 of these type 1a supernovae in 4 colors. These are the light curves. This is just the light history of the supernova as it rises and then declines. And so we were able to, with this set, make a very precise measurement of the expansion rate of the universe nearby at the present time, telling us how fast the universe was expanding. So, as Brian described, by early 1994, a number of us that would form this team had been working hard to measure nearby supernovae, learning everything we could about how to measure their distances. And at some point, we started to become confident that we could take this knowledge and go after the sort of big game at high redshift, the kind of objects that would give us this past information about the universe. And so we set out to, and I emphasize this here, every team needs a credo, and our credo was to measure the cosmic deceleration rate because that's what we thought would be going on. And these are the best pictures I could find. It seemed that we tended to gather in Aspen, Colorado. In Aspen, Colorado, these clothes are what resembles the tuxedo and tails that you wear in Stockholm. And so by 1996, I had gone to Berkeley to work with Alex Filipenko, and we went on observing runs at the Keck Observatory, as Brian showed in his movie, trying to confirm the type of supernovae that the crew in Chile found by sifting through these images. I was also at the time improving these algorithms and also had begun to analyze these pixelated images of supernovae that our team had collected. And I just want to emphasize how challenging this was. Here on the left is the kind of supernova that we had been working with nearby, that we had sort of cut our teeth on. And in fact, my thesis advisor cut his teeth on this one in particular, 1972E. This is a supernova 10 million light years away. And so here's the usual shot before and after. And so the goal is to measure how bright that supernova is to figure out how far away it was. By the mid-90s, the goal had become 1,000 times harder, well, really 1,000,000 times harder, because the supernovae were 1,000 times further away, the ones we were trying to measure by 1996, which means they were 1,000,000 times fainter. There's not often in science you learn how to do something and then try to do it when the level of difficulty has been raised by a factor of 1,000,000. And so this whole galaxy now has shrunk more or less to live in just a couple of pixels. And when the supernova goes off, you can no longer separate the light of that from the galaxy. These couple of pixels have gotten brighter, and you need to tease out that little bit of excess light in order to measure the distance to the supernova. So this was hard work. By 1997, and by the fall in particular, I had been picked by our team to analyze our first really large sample of supernovae, about 16. And having done all the steps in the analysis came the moment of truth where the deceleration rate, which we write in the variable Q naught, set by the supernovae, would then imply how much mass was in the universe. If it was decelerating a lot, if this was a big number, then the mass of the universe would be a big number and the universe would recollapse. So I wrote a simple computer program to tell me what the answer was, and hadn't yet noticed that something very strange was going on. So this is a key page from my lab notebook. When I evaluated what the mass of the universe was, I got an unphysical, nonsensical answer, a negative value. That wasn't even one of the possibilities. It wasn't in column A or column B. It was very strange, and what it meant was, if this term was negative, that really meant this term on the left was negative. That is, the universe wasn't decelerating, it was accelerating. And I just hadn't noticed it. And when you ask a computer sort of a dumb question, you get a dumb answer, which is the universe would have to have negative mass. Now, the real reason is because I assumed this thing that Brian had described, this cosmological constant, didn't exist. And so I quickly realized that the other way to get this number on the left to be negative, for the universe to accelerate, is to have an overwhelming amount of this term on the right, this Einstein's cosmological constant. And so a few days later, I began considering whether that indeed was required by our data, and another calculation showed yes, at what we would call good confidence in the statistics. This wasn't a fluke. At 99.7% confidence, this is what our data was showing. So this was extremely surprising. I assumed, Brian said, what did I do wrong? That was exactly my thought. What did I do wrong? I can't believe we didn't even get close to the right answer. And so I went through a series of checks, but I couldn't find what I had done wrong, and then began to talk to the team about what we as a group had done wrong. And this was a very fun time and exciting, and the best way I can bring my colleagues who are out in the audience back onto the stage with me is to share with you a couple of days of very excited, very tense discussion back and forth over email. And so that's what I'm going to do now. So this was, you can imagine, just upon seeing these results more widely in the team, Alex Filipenko started out the dialogue. Adam showed me fantastic plots before I left for his wedding. Our data imply non-zero cosmological constant. Who knows? This might be the right answer. I should say I got married just a couple days before this, so it was a very exciting time. Bruno Leibengut from Germany wrote, concerning a cosmological constant, I'd like to ask Adam or anyone else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not very sure we are getting the right answer. Brian Schmidt, I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. Bob Kirshner, I am worried. In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care, and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant, only to retract it next year. Mark Phillips from Chile wrote, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry from Hawaii reminds us, who remembers the detection of the magnetic monopole and other gaffes? On the other hand, we should not be shy about getting our results out. Alex Filipenko again, if we are wrong in the end, then so be it. At least we ran in the race. I came back from my wedding, repacked to go to my honeymoon, and typed out a quick email. The results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I have. And I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers after all. And Alejandro wrote, very amusing, if Einstein made a mistake with the cosmological constant, why couldn't we? I could never tell whether this was a vote of confidence or a statement that if you're wrong, you need good company. And then Nick Sunseth wrote, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you're really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. And of course, Nick was, as usual, right. So after about another 6 or 8 weeks of trying everything we could to knock the result down, we felt we couldn't and that we had to come out with the face value interpretation. And we published this paper, Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant, implying that the universe was accelerating at a degree that about 70% of the energy of the universe would be in the form of this cosmological constant, or more generally dark energy. And with the other team reaching the same conclusion, Saul will talk about that, this became the breakthrough of the year for 1998. But just because it was the breakthrough of the year, we didn't stop working. We were very concerned that there still could be something wrong, something subtle. This is the data from the two teams overplotted. These are the nearby supernovae that we've described, and these are the distant ones from the two teams. And as Brian described, the important signal was that the distant ones, the ones coming from the past, were fainter than you would have expected without the universe accelerating. And this was all based on the interpretation that faint equals far, that after we made these corrections, after we accounted for everything we could, that the fact that these supernovae were extra faint meant they were extra far and the universe was accelerating. So we thought hard about what else could mimic this, and others thought hard too. And in particular, Anthony Aguirre, a theorist at Santa Cruz, wrote a series of bracing papers arguing that as weird as the cosmological constant was, what if there was something else weird in the universe? He called it gray dust. This would be a special kind of dust that did not change the color of a supernova, that did not live in the galaxies of the supernovae themselves, but lived between the galaxies. And by looking through this gray dust, we were losing a lot of our light and being fooled into thinking that the supernovae were really far away when they were just faint because of this gray dust. Or it could have been that the supernovae born when the universe was younger were born fainter, just intrinsically dimmer. And so a very powerful test was suggested by around 2000, which is if we could push out and look at even more distant supernovae, we would be able to tell the difference. Because if this dimming due to this mysterious gray dust or supernovae being born fainter was present, presumably it would continue. Whereas a funny thing happens in a universe filled with dark energy. Dark energy only becomes dominant when the universe becomes very large. When it's small, it's more compact. And when it's compact, objects are closer together, and the attractive form of gravity, the pull between objects, becomes more important. And just as acceleration makes objects look further and fainter, deceleration makes them look closer and brighter. So we thought if we could go out further, we would see a transition, a turnover, when the universe was decelerating before it began accelerating. To tell the difference between these, we had to find even more distant supernovae, more distant than we had been able to find in the past from the ground. Which leads me to an explanation of how astronomers often rest on the power of their telescopes getting better and better. Here is the improvement in the telescope over the eye from Galileo through the time when telescopes got bigger, moved to better locations, and got better detectors, and ultimately we placed them into space with the Hubble Space Telescope above the atmosphere so that we could separate the light of a supernova from its host galaxy from the same seen from the ground. And sometimes we're lucky that astronauts go back to those telescopes and improve them with new detectors. And so in 2001, well, in 1997, HISE team members Ron Gilliland and Mark Phillips found what looked like an ultra-distant supernova they called 1997 FF, and I was lucky enough in 2001 to find many more observations of that supernova that were sitting in the archive, having been taken as part of the commissioning of a new camera. And so it was a very lucky set of observations, but even this one indicated it was way beyond anything we had ever measured, and did support the accelerating interpretation of the supernovae, that we could see the universe decelerating before it was accelerating. But this was only a single object, and as Brian said earlier, scientists don't like to rest conclusions on a single object. But the whole story changed in 2002. The astronauts returned to Hubble, and they put a new camera in, the advanced camera, which made it relatively easy to find ultra-distant Type 1a supernovae. And I led a team that from 2002 to 2007 found about 23 of these objects, took their spectra, discovered them by subtracting images, and now looking at this kind of curve Brian had been showing and I showed earlier, the universe has only been accelerating recently relative to a coasting universe shown by the straight line. It's accelerating here, but if you go way back into the past, you see this turnover. It was decelerating, and there's no evidence of some kind of dimming that would have been throwing off our observations. So we were confident in the supernovae, but at this point, it's not just supernovae which argue that the universe is filled with a mysterious dark energy that accelerates the universe. I go over a few reasons. Supernovae were the first to show the universe was accelerating. More recently, we've seen that when we look at photons of light from the early universe, as they cross through the gravitational field of galaxies, they lose energy, they gain energy, and then they lose it as they climb back out. But a funny thing happens to those galaxy clusters. They are pried apart by dark energy as the photons make this trip. And so we see a net change in the energy of the photons. This was first detected in 2003, implying the universe is 70% dark energy as well. We have also seen in observations of the cosmic microwave background that space-time has been smashed flat by all of the energy in the universe, and yet we can only account for 30% of that in matter, which means that there's a 70% missing component, the same 70% seen here and here. And then two other effects we've seen more recently, that the largest clusters of galaxies, which pull new galaxies in, have become less and less effective at doing that because of dark energy. And finally, we've seen a change in the absolute scale of the universe, as first seen at the time of the Big Bang and now measured today. All of these lines of evidence are independent, and yet all of them tell us the universe is about 70% in the form of this funny energy. So at this point, we're pretty confident that it's there. What we're not confident is, why is it there? Brian described Einstein's original idea, the cosmological constant, that you could have a constant amount of energy in space. As weird as this sounds, it's actually predicted at some level from quantum theory. In fact, it's hard to get rid of it in quantum theory. And a consequence of this in general relativity is that it will cause repulsive gravity. As long as there's a lot of it, there is a bit of a calculation problem. When we try to calculate how much there should be, we get a number that has about 120 orders of magnitude too large, but the theorists say they're working on it. It could be that we have a dynamical dark energy. This would be an energy field in space. Think of the magnetic field or the electric field. This would be a different field, and it would be temporary, changing with time. It would work by a similar mechanism, and we have called on this before to explain the first moments after the Big Bang. And of course, it's always possible that we are on the cusp of a revolution in our understanding of gravity, that even Einstein didn't have gravity right, that we have finally seen the failures of gravity as we have gone to the largest scales, and the theorists are working on that too. The observers, however, are working on tests of all three of these by checking the strength of dark energy. Has it been constant like this? Has it been changing like this? Or does it change just when you get to different scales of the universe? So what we're excited about recently is the astronauts have returned to Hubble for the last time and have put a new camera in, and this is helping our studies of dark energy. Already we've been able to improve the precision of the measurement of the expansion rate quite substantially, and we've begun to push even further back toward the beginning of the universe to look for the very first supernovae of type 1a which exploded. So I want to end with a sort of philosophical note. This is our universe. This is the recipe. I think this is one of the great accomplishments of 20th century cosmology, is just to give names to all these objects. It turns out it's very humbling. Only about 4% of the universe is made of the stuff we're familiar with. 25% is dark matter, which is quite mysterious, and 70% is dark energy, which is even more mysterious. These are things that we only see by their gravity. These are things we see by their light. So, why is it that we're so excited about dark energy, or whatever the cause of acceleration is? Well, it's 70% of the universe, so that's a big piece of the universe that you need to understand to say we understand the universe. We've learned it will determine the fate and the origin of the universe. Until we understand dark energy, we can't really answer those questions. But I think what we're most excited about with dark energy is we have two very powerful theories in physics. We have quantum theory, which is sort of our rule book for small objects in the universe, and we have general relativity, which is sort of our rule book for large objects. And these theories don't work together, and we don't try to apply them together. But understanding dark energy requires us to understand both these theories and how they meet. We don't know, as physicists, how to do that problem, so it's very helpful to see how nature actually does it. And so that's why we keep following the dark energy. So I will end there with a summary, and thank you very much for your time.
Okay. So actually that was a pretty amazing account of how Adam spent his early career. I mean, he's still doing important things. I think we have time. Hannah, did you want to play your interview?
I'm not able to get it to load on this laptop.
Not right now. Okay.
On my other, which I can
Okay, we'll do it. We'll do it another time. Then that's fine. So what I think is exciting is that you were able to see the beginning of this story, and also to see not the end of it, because it hasn't by any means ended, but to see that the progress was made in understanding that this acceleration was really happening, it is really happening, and that it requires something extraordinary in the form of dark energy. Now I'd like to show you something quickly. Adam was right that what he was showing was the result of amazing progress in 20th century physics, 20th century understanding, and that extends into the 21st century. I think it's remarkable that we don't actually know what most of the universe is made of, right? So there's dark matter, and I'd like to talk for a few minutes about that. And there's dark energy. Dark matter was first intuited by Fritz Zwicky in the 1930s. Zwicky was looking at clusters of galaxies, and he noticed that these galaxies had velocities within the cluster that were so large that the force of gravity couldn't really bind the cluster together. So why did these galaxies appear to be together in a cluster? The question could have been, the answer could have been, and apparently is, that there was some dark matter present in the cluster that Zwicky's telescope couldn't see, couldn't detect. And it was that matter that actually constituted a large fraction of all the matter in the clusters. And the cluster was really bound, just as it appeared to be, but that we have no idea what most of the cluster was made of. Now, this was put on a firm foundation later on in the 1970s by studying galaxies. So just as the Earth orbits the Sun orbits the center of the galaxy. And in fact, in all galaxies, the stars are bound to the galaxy, and they just, as the Earth orbits the Sun and the Sun orbits the galaxy, these stars orbit the centers of their galaxies. So we actually have all of the same features that you expect. We see that there's a velocity that is equal to the square root of the mass that's attracting the star, I'll call that the mass enclosed, times g over the distance of the object from the center of the mass distribution. And so you can measure v, and you can measure d, and g is just a constant that allows you to measure the mass enclosed. And so you do that. And then you say, okay, let me compare the mass enclosed with the mass that I actually can detect. So you have the mass that you detect. How do you detect mass? Well, you can detect stars, right? And so you can look at the collection of stars in the galaxy, estimate the total luminosity, and then if those stars are similar to the stars we know in our own galaxy, you can estimate what the total mass in stars must be. Similarly, we can detect evidence of gas, let's say emitting radiation, and you can estimate the mass of gas. And so you detect the mass directly. So this is a direct detection. And you can also measure the mass dynamically by measuring the velocities of things that are orbiting in the gravitational field generated by that mass. And those two masses disagree with each other. And they disagree with each other significantly. In fact, most of the mass is not detected. Most of this enclosed mass in the galaxy is dark. This was known to be a great puzzle, and this puzzle has not yet been solved. We don't know what the dark matter is. People have thought possibly it's black holes, possibly it's small planets. We have checked through gravitational lensing that it doesn't seem to be those two things, but I wouldn't say it's 100% ruled out, but it is ruled out with at a fairly high level of confidence. If it's not large objects, then perhaps it's particles. Perhaps there are classes of particles that we haven't been able to detect. And perhaps these particles constitute a large fraction of all of the mass in the universe. So that's a possibility. And the nature of dark matter, establishing the nature of dark matter, is one of the most important tasks that we have ahead of us. We don't know whether this dark matter is in a form that we just don't understand at all, or whether it actually is already predicted in some of our theories of particle physics, or maybe some simple extensions of our theories of particle physics. Maybe we should know that there are particles whose presence we have not yet detected. There are lots of candidates.
The mass enclosed, is that the mass we can detect plus the dark mass that we can't detect to move in the way it's moving?
It's exactly. It's the mass that makes this object move at a speed v. So that is the total, right? You know, when you're just looking to see, for example, if you have two stars that are in a binary, and you can measure the speeds of both stars because they're oriented in such a way that you can get redshift or blue shift from both stars, then you can actually use these dynamical measurements of speed to measure the mass of the total mass of the binary. And it's the same thing if you have one object orbiting another. You can do that kind of calculation. And we know that these calculations work in many, many cases. One of the things people have considered is whether there's something that we don't understand about gravity at very large scales. Maybe gravity doesn't work the way we think it does. But the mainstream consensus at the moment is that it must be a form of matter we don't understand. And what Adam was telling us about dark energy now tells us that there is yet a second different thing we don't understand. So this dark energy is not the same as dark matter. Dark matter was discovered by us through the fact that it exerts a gravitational attraction on other matter that keeps this matter bound. Dark energy is quite the opposite. Dark energy is responsible for the acceleration of the universe, the pushing apart of matter from other matter. As Adam had emphasized at the beginning of his talk, you might expect the universe to stop expanding, or at least to slow down its expansion because of the effects of gravity. However, what their work showed is that there was no stoppage coming in the foreseeable future, that it's not slowing down, it's accelerating for reasons we don't understand. And that this could also be due to the effects of quantum forces we have yet to understand. So these two things that I've written on the board, if you ask yourself what is the challenge that physicists and mathematicians and astronomers and astrophysicists face over the coming years, it's to solve these two things, to understand what is dark matter and what is dark energy. I would say we've come an amazing distance in our understanding as human beings. If any of this is correct, and you know, as we've been following along, there's evidence that we can provide and logical reasoning that provides basis for everything we've said. But we've gotten to a point where the power of all this science combines to tell us that we have no idea what comprises most of the universe. We just don't know. So you're taking an astronomy course, and in the end, what astronomers have to say to you is, we have no idea what most of the universe is. So we can tell lots of exciting stories. We can tell stories about the discovery of reservoirs of water under the polar cap of Mars. We can tell all kinds of fantastic stories, and they're true. Yet, there's a whole component to the universe that we don't understand. And in fact, there are two components that together comprise most of the universe. So I want to leave you with that thought for tonight. And I think you guys are going up to the telescope, so I'll let you get started. Homework is due on Thursday at the beginning of class. I'll be here early. Oh wait, let's do the pizza orders. We did that last time and it worked out well. Let me just pass this around. I'll put it up here. If you want to order pizza, just put your name on this. Over there.
直接输了表情包，我跟同学说对话，然后他给我看了这个表情，笑死！对对对，我打的是那个马蹄嘛，你说对马蹄，然后又看对，没有没有，他重新的听，然后马，我又怎么？笑死，好笑的，下回再。 再有人跟我说我把日本说成了。
How we were all friends.
Oh yeah, yeah. Hi, sorry, do you still have a question on the plate and things?
Oh, I'm good.
Awesome.
I want to make sure. Did I get this one wrong?
Yeah, that's a little too
Did I do it right?
不想说，你要让我讲我的 screen 的 paper 半里边不能说。
Yeah, it should be a much larger ship by the point over 8 inch. It's supposed to be like a 48 inch ship. Yeah, you're just there. I was Oh yeah, I'm sure. Yeah, I'm sure. Yeah, I just don't have a directly covenant or anything. It's not in my office. No, it's not. I'm not giving her 0 or anything. That's fine. Looks like maybe like a small outfit.
So wait, there's the equation, right?
Yes.
That's one of the.
So where does the one come from?
Yeah, and then solving that for lambda. So bring lambda up over. And then C, that'd be over C. Getting around that.
Yeah, I get that piece.
Okay, solid. Yep, so yeah, take that and start with lambda. So that'd be that extra shift there.
Okay, what should I do here?
Let's do this. Can we just send me a quick email and how you solve that problem? If that, I'll give you like, figure that.
I know, we
And I'll try setting out the other solutions.
That's
Does anybody else need to grab their 42s? If not, I'm taking that with me.
I'm gonna ask her because I don't want to like.
Gotcha.
Okay.
Like my friends will just like say hi to
Anyway, I'm gonna go.
For Tuesday, we're going up. Alright. Okay. Oh, no. I'll leave all outside.
Well, that's probably something like a 10 to
Did he grade it?
But is that the math or is that the math per year?
It was with a mass. There's like a certain amount of mass that's falling into like a black hole. What's the amount? What's like the luminosity of the creation? I got that one wrong. But I got a 90, and I got full points on everything for the last. I got full points on everything.
It's right here though. It's in the United States.
Wait, what? Was there no.
I'm not sure where that's from.
I couldn't even write it. I couldn't even write
So I guess I'm a little lost. Let me look at the question. Because
She's been thinking that all day. Is this the same number, question number 7? Or something?
Question number 7, yeah.
we spent a lot of time. My
She's
husband
been
and I, we
working
all
on
got
it.
it wrong because we all worked on it. We spent a lot of time on it.
Okay, well, what is the question we have to
All right,
get back
so
to?
let's open it up.
I'm not sure why this is crossed out of there. I will through that.
So we're turning in homework 3, and we're taking an exam.
On the same day, yeah, we're pressed for time. Yeah, I know. It's not good.
Well, I'd rather have it that way so that I have the to look at still, so I have the practice problems. Homework 2. All right.
We'll practice problems.
So I have these questions to look at when I'm thinking about questions on the test. Because if we turned it in today, I would have wished that I still had it.
Right.
All right, so
If 10 to the minus 8 solar masses per year falls toward a black hole, how much energy will be released per unit of time? So that's, can I write it here?
Oh, yeah.
So, if you want to, you can do it this way, delta M over delta T. This is the mass per year that's going in, right? And so the energy that releases is that amount of mass per year times C squared times some constant, let me call it F. And this F, I would call it right if you said it was anywhere between 0.1 and 1/2. But it's rough because really not all of it gets out, but anywhere in there I would say is correct. So what's the difference between what you did? You didn't say mass per year. So what does this come out to be? It's going to be something between 0.1 and 1/2 times 10 to the minus 8 solar masses per year times C squared. So you had this, but not that.
So how?
So it's 0.1 to 0.5 times 10 to the minus 8 times 2 times 10 to the times 3 times 10 to the 10 squared, right? Divided by 3 times, or 3.15, I should say, times 10 to the 7. We're missing this.
The seconds.
mass per year. So energy per unit of time is luminosity. And I told you mass per unit of time going in, when you multiply by c squared, you're turning it into energy per unit of time.
So
But you
where
didn't
is
put the
this
time
two
in.
from class?
That comes from the fact that if you ask yourself how much energy is released, let's see, how did I derive that? I said,
I have it here.
When the material falls under gravity, it releases the energy, right?
yeah. And it's what it's m dot is the mass per unit time going in, and if you ask yourself how much energy does that release, it's mg over the radius of the event horizon, and that's going to be m dot times mg over 2mg over c squared. So that's equal to m dot over 2 times c squared.
And mg you use the gravitational constant.
Exactly, right.
So does this need to divide it by 2?
No, you didn't put the time in, that's all.
I know, but does it need this
Well,
too?
that's this, so I put it outside.
Uh,
I wouldn't care, I don't know how Ian graded it, but I wouldn't have cared if you said anywhere between 2.1 and 0.5. So 1/2 would have been okay, and so I'm not sure why this was crossed out, but what was wrong with this is that you didn't have m dot, you just had m.
So really, I just need to divide my answer by seconds.
By a year.
By seconds in a year.
Yeah, right.
Okay.
Because that's,
So
that
it's not too
wasn't
crazy.
really off. No, it's mass per unit time,
Okay.
m dot is mass per unit time.
Okay. Okay.
But that's what it is.
So I had the right
It's difference
concept. Alright, I was
between-
like, oh my gosh, I total wrong concept, but I don't.
But
Just
it's,
over
in other
the
words,
years.
and it comes out to be much smaller, right, when you put that in. That's because it's not as if this black hole ate a whole solar mass, right? Or even 10 to the minus 8 solar masses. Every year it does that. It does it over the course of a year. So
Okay.
that's where the denominator comes in.
Okay. And then this 10 to 40% is converted to energy. That's our divided by 2 or your times by
Yeah,
this constant.
that's right. And it comes from
Okay.
here. This is where the 2 comes from.
Okay.
So this is the derivation of the 2.
Okay.
But that's overly optimistic. Usually not all of that comes out.
Okay. Okay.
Okay, it might be in some form that we can't see.
Yeah. All right. Thank you.
Oh, you're welcome.
All right, I have a strange question.
Uh-huh.
And I don't mean to ask this, but how, like, we've been watching everything, and we've been watching the acceleration, and it keeps going out further and further and farther and farther.
Well,
And we just learned
most
today,
of what we
like,
see is
about
the
the Hubble
velocity.
law, and
Uh-huh.
we were looking at it. What makes it so that these things don't just go so far out of sight that you do not see them? Like,
That is happening. That is happening.
if that's happening, then what's this? What are there new stars coming up? Are there new stars coming up so that we can start to start over again?
No, it really is getting that way.
They're just-
Especially with the acceleration, there will come a time when maybe all we can see of the universe is the whole world. I mean, we're here.
You don't see the rest of it at all. Like you just,
And they can't see us either.
if they're just constantly accelerating in opposite directions, they just never come back.
If the universe is flat, what they're saying here is correct. It's a different future to the universe. Remember in the original movie, Brian Schmidt said, I can't imagine this. It's the most lonely, horrible universe. That's, well, just because it means, well, it
Because
means
we could be alone someday.
well, I think all we have the Milky Way and everyone, which will be part of us, and there'll be also other millions or other small galaxies and so forth. But astronomers in those days won't be able to look out and see other galaxies. They won't know that there's the rest of the
Well,
universe.
if today we can look out and see other galaxies that they could not see in the past, that then in the future they would then be able to see even further, or
No, because there's a certain limit to how far, light can't get to us if
Wouldn't
it
we
starts
have-
out too far away.
wouldn't people in our past have thought the same thing, that there was a limit and that they would not be able to see what we see?
Have you read the beginning of Stephen Hawking's Brief History of Time?
No.
I had a long time ago.
It's fabulous. It's like, at first we thought this, and it starts with like, you know, like
exactly.
cavemen. And then we thought this, and then we thought this, and now we think this, and that's just how wrong we are again.
That's what I think that he was saying, Brian was saying up there. Brian was
I have to
saying
say,
we're
you know,
united company.
I think we actually do make a lot of progress.
Oh, we
I
do,
really
but it's like even we can even tell we're just on the tip of like the tip of understanding. Yeah.
Right.
But we're
Oh,
much closer than we were when we thought we were under
People
arrest.
often think that we're, you know, at the end of it, but actually, you know,
No.
obviously, there's a lot we don't understand. But, you know, people in the past didn't think about that because they didn't know the other galaxies existed anyway. They thought that we were the way we're going to be.
Do you feel sometimes as an astronomy professor like challenged, like almost like religiously? Not necessarily from a religious perspective, but just because you sit here and you hear all these things and it makes you really question things and start asking. And does it ever feel like you're having to defend yourself?
Well, wouldn't it feel almost like a neurologist trying to figure out like our brain or trying to figure out like, you know, they don't know what makes a lot of it work and what.
It's the same.
We had a discussion last night about this, and the issue was sort of, well, you know, you can go back and you can understand that the universe had a beginning, but what does that mean? What does it mean that there was a beginning, and what does it mean to talk about time before that? And why is the universe as it is?
Well,
You know, if you don't
we
have
have to make all those
religious-
assumptions, don't we? We have to make a lot of assumptions. Like,
Well, yes and no. I mean, some things we're assuming, but
so
some things we're
asteroids
not.
really hit the Earth and created water.
Okay. Well,
Asteroids, that's
well,
what.
I'm not sure that that's
one
I don't know if
theory.
that's the current version of most water, but yeah, it certainly does happen that comets bring water to Earth all the time,
Right.
every day.
Okay.
But whether that's enough to explain the water we have, that's the part that's not at all clear. So I don't know the origin of water on the Earth. But many of the things that we talk about, and many of the things we talk about here are well established. But they lead to things that we can't understand.
So all this time we thought nothing on Mars, and now all of a sudden they discovered there's water beneath the surface.
Well, I don't know that people knocking on Mars. I mean,
Well, we know there's been water on Mars. There's never been a doubt about that. Because there's all it's in the geologic record of Mars that we can even just see.
Right. Well, I guess we've known for a long time that Mars has ice caps, so that was there, and the fact that there might be water underneath the surface, I think is certainly something.
And so with all of our technology, we don't just go someplace and drill or figure out a way to warm or to cool the water. I mean, with all
They
the
do,
technology that we
you
have
mean in
today.
Mars?
No, like I'm just saying in general, like we haven't been able to, with everything that we know about what we're doing now and the way that we are looking at all of these things, and even with the knowns, I'm really surprised that we haven't tried to figure out.
It's all about funding. We
Well,
could
it's fine.
figure
There's
so
also
much more
limitations.
out if there was like more of a dedicated effort to it. But there really isn't, you know? It hasn't been like, I feel like it's only in the last 5 years that there's been like a national interest. Like you can feel, that's how I feel. I feel like you can feel the populace like shifting. People are like, oh wait, there are planets?
Just
Like,
recently.
oh wait.
Really?
That's how I feel.
See, when I was younger, I felt like there were more young kids who ran around and said they wanted to be astronauts.
Really
than
young,
today.
like when I was a kid. But then it's all died. Like it's been very stagnant for like the last 10,
What
15
about
years.
young kids? Do you think kids have remained interested?
I mean, I've been a space nut and like wanted to be an astronaut when I was a kid. So I have a weird baseline because I've instilled that in my kids.
I don't know, I'm trying to do this project on a children's book, and I was actually trying to explain to my 5-year-old godson, like this book and the idea of the constant speed of light in a book about the speed of light to get you somewhere as far as things go. And he was really more interested in gravity. And he was like interested for like 3 seconds in looking through my telescope at the moon. And he was like, oh, okay. I was like,
Well, 5 is
jeez.
young. 5 is young.
I know, but still.
Right.
Yeah, I would
You know, of
expect
course I
around
wanted to
like
be
8
interested
to
in what I'm
10.
interested in.
Well, it's interesting though, because unless it translates into funding, I don't know that I believe that there's more interest. I mean, there may be more interest, but there's not more funding, really. And I think if there's a big danger of funding being hijacked in the sense that, say this happened actually in the second Bush administration, where Bush actually said, let's go to the moon and then Mars. And he got people together, made commissions and everything. And politically, there was pressure to say, well, we can do that, but we don't have to spend more money than we're spending now. And that's ridiculous, because you have to spend many factors of 10 more money than they were spending then. But there were actually scientists, including Neil deGrasse Tyson, who went along with it and said, but of course they're not practicing scientists, they say, oh yeah, you can do that. And then what happened is that money that was going to research stopped going to research and was siphoned off into all of these directions that had nothing to do with going to the moon, because there was no way any of this money was enough to be able to go to the moon. Only a small fraction of the money is spent on research.
I mean, I work in medicine. Funding is just up there. It's just tough for research for anyone.
But don't you think the privatization of the whole space realm has ignited this interest in?
Well, it may, but I'm not sure that it's positive. I mean,
Well, I don't know if it will actually happen, but I feel like it's got it back on people's thought process.
Well, I thought being able to land a booster on a barge was pretty cool.
Yeah.
Tesla being able to actually land something, or the guy, was it, Ian?
Yeah.
I forget his name, the guy who runs Tesla, but when they shot it off from Melbourne, Florida, and they were able to land that right on a barge, that's pretty impressive.
Yeah, it is impressive. But I think the point is that America hasn't had the investment to do it. And privatization of space is very dangerous in the sense that, people can go up there and put whatever junk they want. And eventually we're not going to be able to get into space anymore, because all of this stuff is in orbit and you can't really get all of these little pieces.
We'll have to have
things.
garbage men. The astronauts will have to go around and apply some kind of velocity to the satellites to get them going.
I mean, all these things, you have screws and nuts and bolts and all kinds of things flying around in space. At some point, it will be impossible to go through that without having a pretty high probability of being hit.
Yeah.
And then you want to go to Mars, right? So you have some private guy who goes to Mars. Well, now we have protocols about not bringing germs and, that sort of thing. You go to a planet where potentially life could be something quite different from what it is here, and you touch down and you introduce something that destroys it. There's no control. As long as any billionaire can do any kind of thing that they think they want to do in space, I don't think it's a good idea. I really don't.
I'm with you, but it's where we're at.
Well, but maybe we don't have to be there. Maybe there are other ways of doing it.
Yeah, it'll be interesting to see how it all shakes out.
Yeah.
I mean,
It's funny,
maybe the Space Force will get us there.
Oh, yeah, sure.
I mean, you never know. Maybe somehow that ridiculousness will turn into a new science and a way to
What are they called?
the Space Force. You haven't heard this?
Space Force?
Yeah.
No.
Oh gosh, just Google it. Google Trump.
There's really nothing.
Well, not before the exam. I feel practice for this exam.
They'll have as much content for you to spend time on before the exam as after the exam.
Yeah, it's not very long.
Is this your adapter? Or is this Ian's?
That just belongs here.
Okay.
Yeah.
All right.
Okay, so I'll just make sure the door is locked after you get so.
And those are not anything that has to do with us, right?
Oh, you know what? Why did they actually
Because I was actually looking for my first. I was actually looking for my first test.
I'm going to send him a note and I'm going to ask him if he left these things.
Okay. Well, I guess we don't need our. You don't need the first exam. Back in. Okay. All right.
Okay.
Is there anything that was just covered in homework 2, homework 3?
Mm-hmm.
All right.
Okay.